The topic is finding shortest path using BFS. Breadth first search. We can find shortest path using BFS. Suppose this is our source and G is destination. We want to reach A to G using the shortest path possible. So using BFS from A, we reach B and D. Okay, from B we can reach A is already visited. So from B we can reach C, and from D we can reach C, G and I. So what is the shortest path? A, then D, then G. A to D, then using BFS we can reach G from D. Okay. Let's see how to implement this. We will simply perform BFS. Okay, let's see the pseudo code first. From a starting source, we perform BFS, and thus we reach the destination, and this is the shortest path. For doing this, it is convenient to use adjacency list structure of graph. We may use adjacency list. Okay, we will also use Q. Suppose from this point we reach this point. Okay, using Q. So this is point 1 and this is point 2. So parent of point 2 is what? Point 1. From 2 we can reach 3. So parent of 3 equal what? 2. Now if we track them reverse, so suppose x equal 3 is destination, so parent of 3. Now again x equal parent of x, while source not found, so we can reach source and we check the path via X. Okay, this is how we build the path. We maintain visited list. Okay, suppose we visited 1, 2, 3. So 1, 2, 3. If we visit other path, we also keep track because it allows us to avoid cycle in BFS. Okay, let's see the code directly from collections, import default dictionary. We create adjacency list, default dictionary. What is the type of values in key value pair? This is a key and value will be list of adjacency vertex. We also maintain parent default dictionary. It will be type str string. Now we build the adjacency list like this. Edges are given to us. Okay, it is pre-given. Append. And we assume this is undirected graph, so neighbor in both way. We have built the adjacency list. This is the queue we use for BFS. This is the visited list we maintain to avoid cycle or duplicacy. This is our source. Here it is A. It may be another source. Destination given G. Now, if source not in adjacency list keys, so this is an invalid source because we have no way to travel from the source. So if source not in adjacency list of keys, this is a dictionary key value. So keys means all keys, set of all keys. Source is invalid. Okay. Else, if source is valid, we append it to the queue. Also, this is now visited. So visited.append source because we have visited the source as we added it to the queue. Now while q is not empty, that means while q. Okay, we pop from the q x equal q dot pop 0. That means we pop the first element from the queue or 0th element. Okay. It is coming from here to here. I is the direct neighbor of x, I1, I2, I3, I4. Okay, so for I in adjacency of x, direct neighbor of x, if I not in visited, okay, we add I to the visited list. Also, as I is not visited, we append I1, I2, I3, etc. if they are not visited to the queue. Okay. Also, what is the parent of I1? Parent of I1 equal x. So x. Also, okay. So this makes sure the all vertices are visited in a BFS manner, and visited is the output of BFS traversal. Okay, our BFS is complete. We got visited and parent. Source, destination, path equal D. What is the destination? We travel D by its parent, then this parent to source by using parent dictionary. While destination not equal source, this is a we use while loop D equal parent of D. Now x parent P, D holo destination. So parent of D1, then D2. So parent of D2 is D1, then P. So D equal parent of D. So it was pointed here. Now D equal parent of D. Now D is pointed here. Okay. Again, after this while loop, it will be pointed here. If P equal source, then this loop stops. Okay. So we get the path, it is in reverse. Now this path means destination to source, but our output should be source to destination. Just we inverse the list. We print visit, we print path. Okay, this while loop stops when source is found. Okay, so this is our code. Output. I previously showed the image. So V equal A B D C G I E H. Path equal A D G. So we reached from source to destination. Complexity. Big of B plus E. Because this is a breadth-first search, we visit all the vertexes. Maximum, suppose all vertexes are key, then it will be V and is neighbors, and each neighbor represents a connection or edge. So total time complexity big of V plus E. Thanks.